And here we go, guys. Question 4. Let's go. So, what do we have here? So, Sarah was studying the relationship between rainfall given in R millimeters and humidity in H percentage. So, I can already see that there's some sort of correlation regression problem coming up in the UK. She takes a random sample of 11 days from a specific month, so May 1987, for Luchars. I hope I said that right, guys. Anyone from there, forgive me. From the large data set. She obtained the following results. So just having a quick look at the results for 2 seconds, you can see that for humidity, it seems to be quite consistent between 80s and 90s. So, of course, you're in May, so it's summer. So you expect this to be the case. So we expect it to be quite humid. As for the rainfall, it seems to be quite consistent, like very low, 1 and 0. But, oh wait, hang on. Yeah, you got 20.6, which is obviously messed up. And yeah, so more or less to summarize, you should try and spot that 20.6 is obviously going to be an outlier, which will come up in a question anyway. So let's keep going. So Sarah examined the rainfall figures and found out that the first quartile, so out of the 11 days, the first quartile of it was 0.1, the medium was 0.9, and the third quartile was 2.4. Now, a value that is more than 1.5 times the interquartile range is above the third quartile is called an outlier. So they actually define it for you what an outlier is. In other words, I wrote it here. So it's basically 1.5 times the interquartile range. And remember, the interquartile range is the difference between the third and the first quartile. It's the range between the upper and lower quartiles. Makes sense? And of course, it's above Q3, so plus Q3. Now, show that the value 20.6 is the outlier. Well, first things first, we have the value Q3. We have 1.5, and IQR is just 2.4 minus 0.1, so 2.3 here. So you just plug all this in, you realize you should get 5.85, and well, any values above 5.85 would be considered an outlier in this experiment. So 20.6 is clearly above. That's what you should say. You can say clearly 20.6 is above this formula, which is above 5.85. Simple. It's kind of obvious anyway, but we have to use mathematical proofs. Now B, give a reason why Sarah might exclude this day's reading. So we're talking about 20.6. Well, from what I gathered, if you're going to put a data set, usually when you record, you keep. So in many cases, you should choose, if you choose to include it, you keep it because the data set could be relevant and it helps possibly build a complete picture, even though it could be an outlier. However, to exclude it, which is quite simple, the value itself could just be a mistake or an error. That's really it. It could have been a typo. It could have really been 2.6, like 2.4, but we don't assume that. That's really it. Now, next one. So Sarah decided to exclude this day's reading. So now we only got 10. So she's going to exclude it. So 97, 20.6 is gone. So we only have 10 pieces of data. And she decided to draw the following scatter diagram for the remaining 10 days. Okay. So very easy. You got humidity on the x-axis, rainfall on the y. So we're probably going to guess that y depends on x. So rainfall depends on humidity. So looking at this one, it's hard to probably visualize, but this is sort of like a positive correlation, maybe. And what does this tell us? Well, we have to firstly give an interpretation of the correlation between rainfall and humidity. So what I just said, if as humidity increases, then the rainfall increases. So as H goes up, rain goes up. So in your answers, it's best to say that this diagram, you could say firstly that there is a positive correlation between humidity and rainfall. And in turn, this implies that as humidity increases, rainfall is expected to increase. It's kind of weird, isn't it? But yeah, that's how it works. Now, next one, number 4. So the equation of the regression line of R on H for these 10 days is given to be R equals minus 12.8 plus 0.15 H. So just like your standard straight line equation. So this is talking about this line I just drew. Okay, something like that. Now, give an interpretation of the gradient of this regression line. So I put the answer already here, but just to understand, we're talking about this figure here. So because we can see that the gradient is 0.15. So what we have to understand is that for every unit of H, you get a total rainfall of, you get an additional 0.15 millimeters of rainfall for every 1 unit of H. So that's what you have to understand. Every time you increase this value H, the total rainfall will also increase. So here is an example answer. So an increase of 1 unit or 1% of humidity causes an increase of 0.50 millimeters of rainfall in this specific calendar. So it's good to specify where. This is only specific to May 1987 because that's a data set we have. So of course, she only took a random sample of a days fixed from May. If you took the whole year, then this would obviously not apply. And yes, I should have said May 1974, Luchars. Again, if I'm saying it right. So that's what you should do. Secondly, actually that's it. And yeah, I gave an example. So the one way to understand is that it's best to use values between the ranges. So humidity, we know that humidity lies between what? Like the 80s and 90s. So just plug in values of 90. I just chose 91 and 92 just to show that there's an increase of 0.15 as you go by 1 unit. Not necessary, but just to have an idea behind this. Now E, comment on the suitability of Sarah's sampling method for the study. Well, this is not suitable for everything because remember, we're focusing on the specific month and year, so May, and that specific region, Luchars. So we could say that it's not suitable for other months and locations. Of course, it's only suitable for that particular month. And only 11 pieces of data were used solely in May. Or in this case, I should have said 10, because we used 10. We ignored the other one. So it's not very reliable. It's only suitable for May and between those ranges. Now, suggest how Sarah could make better use of the large data set for a study. Well, I said that large data set should include other months and regions. Because in general, to improve your data, it was always good to consider every single. It depends how far you want to go. If you want to include every other month and region, then you would have a complete or clearer picture. So doing so, this would improve the accuracy and reliability of the data. Then this is a good use of using a large data set. She could use the company's data set, of course, a large data set, and consider data sets from various location months. That's literally all you need to do. And because it's only 2 marks, this should give you more than at least 2 marks or more. Well, 2 marks. But yeah, that's really it. I mean, if you guys got any questions on this, feel free to drop me a comment, because this is all theoretical. So we're not really doing any proper maths here. This is all your understanding on correlation and regression. That's really all it is. But yeah, let's go. Let's how about we move on to number 5 now. Oh yeah. Oh, now this one's kind of annoying. I can't lie. Now, when I wrote this here, there's a specific calculator that you guys need to buy when you're doing the binomial distribution, or normal, or Poisson, or whatsoever. And this is the FX991ES. So I made a little link to Amazon. I could put this on. I'll attach this calculator actually on the description comment. And you guys should really buy this because this includes everything you need for the new specification exams. So the old ones unfortunately doesn't work, and it's recommended to buy this calculator. So keep an eye out on this one. Otherwise, you cannot solve the first question. Was there questions? Yep. Otherwise, you cannot solve part A because we're given a binomial distribution with n40 and probability 0.27. You cannot solve this question. You can, but it'll take you a long time. These questions are made for the calculator. Okay. So I would have a breakdown on this one, but it's best. The general idea is that because you got a probability which is greater equals 16. We have to convert into something that is cumulative. So it'll be 1 minus less than equal 15. So instead of 16 and up to 40, it'll be 15 and less to 0. And in the calculator, this is known as the cumulative probability, which is available in this calculator. Otherwise, you're going to have like 15. You go do 15 different calculations if you do it manually. Unfortunately, you cannot use interpolation if you guys have thought about that. Because in the tables, and I also want to do this really quickly, the tables only record probabilities in going up in 5%. This one only records this one has a probability of 27%, so that is not on the table. So again, don't use interpolation because I tried it and you don't get the correct answer, which is 0.0509. You get 0.0618, which is close, but no cigar, guys. But yeah, that's it. But anyway, besides that, buy this calculator and it should be fine. But anyway, skipping part A, the rest you can do without calculator, thankfully. So what do we have? So it says past records suggest that 30% of customers who buy baked beans from a large supermarket buy them in single tins. Now, this new manager suspects that there has been a change in the proportion of customers who buy baked beans in single tins. So keep this in mind. So we got a probability of 30% who buy baked beans, and that's fine. And now we got a random sample of 20 customers who had bought baked beans. We also know that another key thing to note here is the wording. So sometimes you might hear the words that, the manager suspects that there has been an increase or a decrease. In this case, he uses the word change. So he doesn't know if it's increase or decrease. Hence why when you get to part B, you'll see. So for part B, write down the hypothesis that should be used to test the manager's suspicion. So all you have to do is say, okay, let's get a null and alternative hypothesis. So H2 and H1. We know that the null is 30%, so P equals 30% or 0.30. The alternative would be P doesn't equal 30% because there's a change. So it's not greater or less, it's not equal. So in other words, this is also known as a two-tailed test. Okay, because it could be up or down. So anyway, that's done. Part C. So using a 10% level of significance, okay, and this is two-tailed, so we're looking at 5% because it's halved. It's 5 on the left, 5 on the right, so up and lower. Find the critical region for a two-tailed test to answer the manager's suspicion. You should state the probability of rejection in each tail, which should be less than 5%. So first things first, we need to know what our binomial distribution is. We know that n is, the sample size is 20, so n is 20, and we know the probability is 30%. So now we need to, the key idea is to find what value, or what sample do we need that will guarantee probability less than 5% on left and the right side. So diagram wise, it looks a bit like this. So suppose you have this entire sample. We want to find it on the tables a percentage less than 5%. So let's have a look. It's probably best to go through this step by step. Okay, so firstly get this table out. N is 20 and P is 30%. So on the tables here, guys. So I've got it ready. So look at the binomial table. And if you guys are not sure where this is on the Pearson Edexcel website. They have a formula table ready for you guys. So okay, let's look at n is 20, perfect, and then the probability value was 30%, so 0.30. So you scroll down, and now we find a probability value which is less than 5%. So we see that we have 0.0355. This is 3.55%, so less than 5. But afterwards it's bigger than 5, it's 10%, and so on. So that means we know that the first critical value is less than 2, which is 2. Remember, this is a cumulative table, so this is probability x, or y in this case, less than equal to. Another thing we'll spot now, and because it's two-tailed, we have to look at the right side. So remember, just think of it as a bell shape. We have to look at the remaining 5%. So if probabilities go up to 1, we need to look past the 95%. Okay, so between 95 to 100%. And if you scroll down, you'll see that if the probability value here, 0.9520, is literally just above 95%. So this is the last 5%. So yeah, you see that this value is literally the remaining 5%. But if you think about it, because this is a cumulative distribution, this is telling you that the first, 9 values accumulate 95%, over 95%. So that means the values after 10 will accumulate the values less than 5%. So we're going to have to look at probability y greater than or equal 10. So remember, it'll be these values after, yeah? So that's it. So that means we have a critical region, which is y less than 2 and y greater than or equal 10. Whew, you know, guys, stats, it's okay, but it takes a while to really break down. But yeah, that's what we got right here. Okay. Whoa, sorry, I just got a crazy neighbor, just God knows what he's doing. Okay, D. Find the actual significance level of a test based on your critical region. So this is dead easy. This is just basically the probability values of what you just found. So that's what it means by actual significance level. So if we realize we had the probability y less equal to, it was like 3 point something, wasn't it? It was this value here, 0.0355. So that's the value for this one, 0.0355. And probability y greater than or equal 10. Well, we know that when y was less than or equal 9, it was 0.9520. So greater than or equal 10 would be 1 minus this value. Okay, so 1 minus 9520. 9520. And if you add them all up, if you solve this, add it to the first, you should get this value here, which is again less than 10%, but they want a percentage. So make sure you get the percent, or else you could lose a mark. Alright, so far so good, guys, almost done. Now, one afternoon, the manager observes that 12 of the 20 customers who bought baked beans bought their beans in single tins. Alright, comment on the manager's suspicion in the light of this observation. Well, this is all based on the critical region. And remember, if you look at the part C, we're talking about the critical region to test the manager's suspicion. Well, if it's above 10, then we can safely assume that the manager's suspicion is supported. So if for anyone that has 10 or more people, or 2 or less, then we say yes, we support. And that's it. So we say 12 greater than or equal 10, all good. Now finally, later it was discovered that the local scout group visited the supermarket. So remember, these are not random. So these are specific people. that afternoon to buy food for their camping trip. So it wasn't random. They know what they were doing. Comment on the validity of the model to use to obtain the answer to part E, giving a reason for your answer. This is very straightforward. One thing you need to know about binomial distribution is that the sample size is random. And you'll spot the words here, a random sample 20. If you have a random sample, it's binomial. This one is not random, so it's not binomial. And that's it. That's all you have to say. Binomial is not valid as it's not a random sample. And that's it, guys. I hope these stats questions helped. And after this, we'll be looking at mechanics. So hit me up and let me know what you guys think. And otherwise, I shall see you guys next time. Ciao.